Okay, I'm Dennis Derickson, professor here at Cal Poly. I think I got my start in electronics because in 1975 I got my first amateur radio license in novice and learned the code, and I thought that was this mythical communication over the ether just fascinated me, and I think that really changed the direction of my career early on. So. Uh, I was WN0ROL, then I was WB0ROL, and my call sign now is AC0P, which I think I got around 1980. I think I got that call sign. So uh, the high frequency or just propagation in general has been very fascinating to me, and so I knew it from direct experience, but I had some idea what's happening from a physics point of view. But this book called Understanding Radio Propagation by Michael Burnett, AF7KB. It's a paperback book that you can get on Amazon. It's really easy reading, and I thought that was like the best book, like $10 or $15 to buy this nice book. And then there's a lot of stuff available on HF radio propagation, and I stole a bunch of slides from this Australian Radio and Space Services presentation. So there's all these bands going from 1 megahertz to 3.5 to 7 to 14 to all these high frequency bands. High frequency is generally 3 to 30 megahertz, but we have this 1.8 megahertz band too. And then we've got the VHF from 30 megahertz to 300 megahertz, and then we got the UHF 300 megahertz to 3 gigahertz, and all the way into microwave and millimeter wave. And of all those frequencies, propagation is a little different between all those different frequencies. But I was always fascinated by these lower frequencies, especially, and also fascinated by how some times of the day, even at VHF, I'm able to go surprising distances. And so I remember I was in Minnesota, and there's certain times of the day and certain conditions where all of a sudden my 2 meter radio on single sideband might only have a distance of like 20, 30 miles, but then all of a sudden it opens up to thousands of miles. Just this weird phenomena like that. And so what's all going on with this propagation stuff? Yeah.
We get full screen, please.
Okay.
And maybe dismiss the notification up there as well. Thank you.
Okay, let's get down to here. Full screen there. Okay. So all these different bands, all these different propagation modes. So first start some of my direct observations. So there was a time a few years back that I got involved with these VHF, UHF propagation contests. They're typically in July, August, I think they have one in January, where people go out in the field to the top of mountains and try to point their antennas and see how far you can go in the VHF, UHF spectrum. And then the whole world is connected by these things called grid squares. And I think I'm Charlie Mike 98, I think is right.
1795.
CM95QH.
I mean, maybe I'm CM 95 too. Yeah. So these grid squares that we're in, and so in these VHF UHF contests, you try to see how many grid squares that you can contact, and these are at frequencies above 30 megahertz. And so, example, I went on top of the Cuesta Ridge and set up antennas there. I had to get all my antennas ready. Nano VNAs were just coming out when I did this presentation, and they were just amazing that you could get a really high performance vector network analyzer for $100. And so that really made it much easier to get your antennas figured out if they're working well or not. So I got my 2 meter, this is my 2 meter 5 element dipole, I mean Yagi, and then so anyway, I had my car there and I got these masts that are telescoping, and so I have my my 6-meter dipole, and I have a 2-meter beam right here, and above that I have a VHF, UHF vertical. So I had all that, and I load up my radio equipment in the back of the car. I think at an ICOM 9100, and I was able to. It's not like the contests in the VHF, UHF are not like field day where you got these pile-ups or something like that. You got a few people here and there, and you have common calling frequencies. And when you hear somebody, you're thrilled, you know. And so in a whole contest, I might make 30 or 40 contacts or something like that. So it's a very different kind of contact. This was something that have everybody seen this websdr.org?
It's
And
awesome.
so they have different software-defined radios all over the place, and you can actually hear yourself. You know, so we can transmit, and there's one in Half Moon Bay. I think there's one in Utah, and so you can test your own propagation. You can put out a radio signal, and you can listen to yourself at a bunch of different locations. And everybody with the SDR, everybody can share the same bandwidth. So there can be 10 people logged into the software-defined radio in Half Moon Bay, all listening to the same spectrum at the same time. And so it's just interesting to see at different parts of the world, you can just go to these web SDRs and see what are they hearing at that point in time. So it's a fascinating way of checking out propagation with these web SDRs all over the world. So a couple of questions right here I asked myself. Why is my VHF UHF signals able to travel 100 or so miles? And why do my 1 to 20 megahertz signals be able to travel thousands of miles sometimes? You know, why is that? What's going on there? So the key thing right here is that we have this thing called the ionosphere. And the ionosphere is a place quite high up, and there we have the sun putting out UV photons, and when the UV photons hit our atmosphere, they can separate the electrons from the nucleus, and so we're going to have free electrons really high up in there. And so the basic idea is that at the ionosphere right here, you have positive charges, which are kind of heavy, and electron charges, which are not so heavy. And so if you can send out a radio wave right here, we have this electric field that's in your radio signal, and there's this equation: force equals charge times electric field. So your electric field here from this antenna is going to say, hey, I'm going to move you. I'm going to wiggle you back and forth. Now the positive charge is kind of massive, and so we don't really move that positive charge very much. But the electron is very small and not so heavy, and so we're going to wiggle that electron back and forth. And so that's kind of like an antenna in the sky for you. So a regular antenna at the ground right here, you know, what you're doing is you're taking your coax cable and you're kind of accelerating charge back and forth, and that acceleration of charge is what causes the radiation. And so what you're doing right here is you're sending up something into the ionosphere, you're wiggling electrons, and that's kind of like you have a virtual antenna up there in the ionosphere that re-radiates the wave down. The thing that changes though is that if this is slow, going back and forth, the ACE field, then these electrons have time to move. But if you go higher and higher in frequency, if your electric field is going this way, then this way, then this way, then this way, if it goes so fast, at low frequencies, the electrons will move like this a lot, because there's a lot of time to do that. But at high frequencies, there's just not enough time, and so the electron motion gets really small at high frequencies, and eventually it doesn't respond at all. And so that's kind of like the basic principle of what happens in this ionosphere right here. Go ahead. What's that?
What ions were
there? I'm not sure that was that material here, but it's the electron itself that we're worried about. You know, where ionizes from. I'd have to look on these presentations to see what molecules there are, but it's the electrons that you're wiggling back and forth.
So Do you mean, when you say wiggling, do you mean you're like charging it and then and it absorbs some energy and then it releases the energy and releases?
Well, it's more like, it's just, this is the basic concept right here. So if you have an electric field, E, and if you have a charged particle, which is negative charge right here, there's a force on it. And so if you just had a DC field that's not changing, then the electron will just kind of start accelerating right here. If you have a constant force equals mass times acceleration, it would just start accelerating up and up and up and up, faster, faster, faster. But we have an AC field that the E field is going up for part of the time, going down for part of the time. And so the E field, when it's in this core thing right here, the electron will start accelerating up, but then you turn the electric field the other way, and then it will try to accelerate down. But it's only going to move a certain distance before it changes direction. So at low frequencies, it has a lot of time to accelerate this way, then a lot of time to accelerate that way. But at high frequencies, it's going back and forth so quickly that essentially at high enough frequency, there's just no motion in the electron at all. It just stays stationary.
So does that mean it doesn't propagate the signal anymore?
Yeah, it's just like it's not even there anymore.
Okay.
It's because to accelerate the particles up and down, it actually takes energy. And so there is going to be some absorption also in this phenomena. When you're moving these, it takes energy to move back and forth. But in this case, when you take an electron up and down like this, it's actually generating a new wave that will re-radiate down to the Earth. Yeah.
How homogeneous is the ionosphere? Like, does it depend where you're at on like
Oh,
poles or?
It is this is just a big blue line right here in this presentation says the ionosphere. But when you're an ionosphere guru, then you'll divide it to a whole bunch of layers, A, B, C, D, E, F. And so there's a lot happening in all those different layers. And so on the top of the ionosphere, you have a lot of electrons that are free. At the bottom of the ionosphere, you have no electrons that are free, just a few of them. And then part of the issue also is that that electron right there, no, right here is electron right here, that's on the top ionosphere. How long does it live before recombining with a positive charge? So initially, that electron is associated with the nucleus, the positive charge initially. Then if a photon comes in from the sun, so sun comes in, sends photons right here. And then that photon energy is absorbed, electron becomes free to move around. But it could, if they're really far apart, then it's not very probable that the electron and hole are going to come back together and become neutral. If they're really close to each other, then they might collide and become neutral again. But really, when the electrons are all by themselves, that's when we get this electron motion back and forth. And if they are far apart from their positive charge particles, and if there's enough of them too, if you don't have very many of them, your signal will be very small. If you have a high density of electrons that are living a long time, then you get a lot of this re-radiation in the ionosphere. But yeah, as we go along here, there's a whole bunch of different layers within the ionosphere. Now, my VHF UHF signals, they will most of the time just kind of head out to space or follow the Earth a little bit, but they're not going to interact with the ionosphere very much because they're such a high frequency. So that's kind of like the big picture of what's happening in the ionosphere. There are measurement tools that will, it's like in vector network analyzers, you have this thing called S parameters, and then there's actually a time domain view of S parameters. You send out a wave, and then some waves will be reflected back. And so in vector network analyzers, you can plot out reflectivity versus distance also. And so you can, if you have a broadband antenna pointing straight up, you can actually measure reflectivity versus distance and kind of get a view of what's happening in the ionization versus distance. Yes.
In the previous slide, there was the electromagnetic waves following along the surface, like it looks curved. Is that
Yeah.
actually what happens? How does that?
Well, there's a couple different things happening there. when I do UHF propagation or VHF propagation, there's this phenomena that let's just look at fiber optic communication right here. So in fiber optic communication, you have a waveguide. You're going to have waveguide with index refraction equals 1.503, and that's silicon dioxide with doping. And then you have something right here that might be n equals 1.500. Index refraction is the speed of light of propagation, so velocity equals speed of light over the index right here. So if you are in index 1.5, that means you're about 2/3 the speed of light, something like that. And with Snell's law, you get this phenomena that if you have a certain degree of angle right here, you get this total and tonal reflection. And that's how fiber optic works. So if you kind of just did there's also something called a graded index lens. A graded index fiber cable has a gradual tapering instead of the index being like this right here, where it goes higher in the middle, lower on the outside. Maybe it's kind of like gradual like this. It's kind of like gradual index refraction. So if you draw a line down the middle of that, you have something kind of like what happens on the Earth. On the Earth, you're going to have the ground right here. And then you're going to have high density air. And then you have low density air. And so it's kind of like this waveguide. So the waveguide is like a waveguide that's going to slowly bend it like this right here. So if you send a wave like this, it will kind of bring it down like that. So you get this waveguiding effect because at the Earth ground, you have high density, which means you have a little higher index. If you go up, you have a little lower index. But then there's other weird phenomena too, where you get a weather condition where you maybe have temperature inversions and things like that, and you can get ducting. You get a really good fiber optic cable essentially like that. And so there are times where you get this low index, high index, low index. Maybe this is the sea level, and maybe you have like this this air right here. Maybe this is a little denser air, and this is less dense. This would be like a cold, and this would be hot and hot right here. And so you actually form like a fiber optic waveguide right in the sky. And so there are times that if you are at the right height, if this is the Earth right here, and this is like a cold section right here, and this is a hot section, and this is a hot section right here. And if you're on a mountain right here, and you have your radio right at this level right here, and then this is Hawaii right here, it's a mountain right here, and you have your radio right there. There are conditions where you will get waveguiding over thousands of miles if you get the right temperature inversions kinds of things. That it doesn't happen often, but when it happens, you can get just really hear all the FM radio stations from Hawaii coming out here in the West Coast as an example. So that's one phenomena that can happen, is that we just get this general bending due to the fact the index refraction goes down as you generally go up. It forms kind of like a partial waveguide.
Do you want to take a quick break so we can get?
Yeah, let's do that. Let's do the quick break. Yeah.
Feel free to grab some pizza.
Yeah, grab some pizza here. I'll grab it here quick. Okay. The ionosphere, okay? It's not just one thing, it's a continuum of things. So here on the vertical axis, we have altitude going from sea level up to 500 kilometers. And so the CubeSat we launched a while back is up there, probably around 500 kilometers, isn't it?
Mm-hmm.
So you have the Sally satellite going around the Earth. What's the period of the going around the Earth?
90 minutes.
90 minutes, okay. Uh, so it's actually going through the ionosphere. And so that provides some drag, I think,
Mm-hmm.
hitting all the helium atoms up there. Huh? Um, so on the horizontal axis, we have free electron density. It doesn't talk about total electrons. How many free electron charges do we have per centimeter per centimeter cubed? Yeah. And you can see that the maximum number of free electrons is up in these layers called the F layers. And those are the layers that we uh, really get our long distance propagation from, but only at low frequencies. At high frequencies, as I said on the board, the electrons don't move. If you have electrons, if the electric field is so fast, the electrons don't move, then there's not going to be any re-radiation in those layers. And in the F layers, I'm not sure, but there's a certain time to live. If an electron's freed by a photon coming in from the sun, there's a certain amount of time that it will live before it recombines with a positive charge. And that recombination time is really an important parameter. On some of the lower layers, like the D layer down there at the bottom, there might be some photon. So as you have this high energy photons coming from the sun, you get a lot of, it first starts hitting the atmosphere saying, I'm going to create lots of electrons, but then that will suck up photons. And by the time you get down to the E or D layer, there's not much left for UV photons anymore. And you need high energy photons to liberate electrons. If you just have low frequency electrons, that's not going to do it. So the higher closer to the ground you get, the fewer free electrons you get. And also the thing that changes too is if you're at the F layer, the average time to live for an electron in the F layer is probably pretty long, but because it's not very dense, the material out there. But if you get down to the D layer, the average time to live for an electron after it's created from a UV absorption event is not very long. So the D layer is less useful for propagation, one, because it's much lower, but also because the electrons don't live very long, so it's not that efficient at moving electrons back and forth. So the F layer, and so you can see from this graph that during the day when the sun is shining in the atmosphere, you get lots of electrons. But then at night, it does reduce. Here it goes from peaks of 10 to the 6th, and at night it goes down to 10 to the 4th, 10 to the 5th. So at night, HF propagation is not as good at night. And it kind of, it's interesting that the frequency at which you get that re-radiation has a certain maximum usable frequency. And that changes with the density of the electrons and the lifetimes of the electrons. And so generally at night, then the lower frequencies work well for long propagation, but the higher frequencies don't work so well because the electron density is so much. And there's a thing called plasma. Plasma is just a gas that has a lot of charged particles in it, both uncharged and charged particles. And plasmas are useful for like deposition in clean rooms or something like that. Oftentimes we make plasmas of free electrons, and we make nice things using semiconductor processing. And that is kind of happening in the sky in real time too, the creation of charged particle plasmas. So this is just another one. Just shows how at night the electron density goes down. During the day, the electron density goes up. And then we have this this weird layer called the E layer right below the F. And so I think typically what happens is that at night when the F layer becomes lower density, you get these electrons that are moving around like little clouds. electron clouds that kind of gather together. And typically during the evening time or maybe early in the morning, you get these when you're transitioning from day to night, you get these kind of like little clouds of electrons at lower altitudes that kind of travel around. And so if you happen to be lucky that between you and a destination right here, there's this little cloud of electrons at the lower E layer, you can do a nice bounce off that. And so that is like when I was in the Midwest and I was at 144 megahertz, typically I would have just a few, maybe 50, 60 mile range with my 144 megahertz radiation. But some of these E layers can have quite dense electron densities. And when you happen to have an E layer that kind of goes over you, between you and the destination, you can go thousands of miles at even at 144 megahertz with these sporadic E layers. And so it used to be that we had when we had analog TV, there was a radio stations in the VHF like 50 megahertz like there was a radio station at like 60 megahertz, a TV station. And so I would always watch and I'd turn the TV to like the channel 2, which was like 60, 70 megahertz. And then when there were times where all of a sudden TV stations from all over the US would show up on my TV and they all be crosshatched and interfering with each other. And when that happened, when channel 2 on the old analog TV days, when you got all these stations coming in from all over the place, we go, okay, we got sporadic E. Then you go on to the 50 megahertz ham radio band or the 144 megahertz radio band, and all of a sudden you can communicate thousands of miles when these sporadic E clouds kind of came over in different parts of the country. And it's somewhat unpredictable. I mean, there's different times of year where they're more often formed, but the sporadic E is something that was really, really fun for making long distance connections in the VHF, UHF band. Yeah.
How long would a sporadic event last?
Typically, half hour, something like that. But some could last longer.
Yeah.
Yeah, that's my experience. I'm sure there's more publication on that. So all these layers. So what's going on there? So the density of electrons is very important. The lifetime is also really important. How long does a electron live before it gets recombined? And also, when you get the electron density changing very fast versus height, that's also very effective in getting a better long distance propagation. And then there's this thing called the sunspot cycle, and every 11 years we get more electrons per unit centimeter cubed in the F layer, and then later on, sometimes between the cycles, we get less dense F layers, and so that's a very important. And where are we in the sunspot?
Currently, I think just past the peak or somewhere near the peak, I'm pretty sure.
Check out a handbag board or whatever it is.
Yeah, every 11 years it changes. Yeah.
So when we get more sunspots, it gets less sporadic because there's less radiation.
We get higher electron density when we have a sunspot cycle happening, I think. But that kind of brings me to something I don't quite understand. I think in the model I've been presenting to you, I have UV photons from the sun coming here to the Earth and ionizing electrons in the F layer. Now you'd think that would be pretty much independent of sunspot cycle, right?
Or like an opposite, sunspots are when it's colder.
When sunspots
are like when it's colder.
colder, okay.
Yeah, the colder regions of the sun.
Yes, and why would it send more radiation?
But the sunspot cycles, does it really change the power per unit area of light hitting us, or is it what's changing on the Earth? I don't know that.
It's coronal mass ejection.
Yeah.
That would matter. So
Yeah, the solar flare.
the sun's
Right. So sunspots are discontinuities in the sun's electric field, and sunspots will create these localized loops of the magnetic field, sorry, and the ions or the plasma on the surface of the sun will follow those loops, right? Because the plasma is charged,
Okay.
and it will follow the broken magnetic field loops, or sorry, the localized magnetic field loops over a sunspot. And as the sunspot shifts, it'll break one of those loops.
Okay.
And since the plasma is contained within that like magnetic arc, it will like release all of that towards.
Okay. So the things that matter to us are the free electrons then. So
When that sunspot breaks,
Yeah.
that will release particles.
yeah, okay. So our ionosphere can be supercharged then.
Yeah.
That we get some of our particles created every day just by the fact that UV photons are coming in, and then in the upper layers,
Ionizing photons, not just UV.
yeah, ionizing photons come in and make
Not just UV.
charge up our F layer, so we have a good electron density in the F layer.
Also,
Go ahead.
the peak of the solar cycle was 2 years ago. So
2
we're
years.
still riding the
Okay.
it's pretty good for Ham. It's not gonna be pretty good in what the solar cycle is 12 years?
11.
11? Yeah, something like that. So in another 5-6 years it'll be kind of bad.
So I guess we can get our electrons in the F layer by two mechanisms. One, UV photons ionizing particles in that layer, or we can just get particles being transported from the sun that will accumulate at the F layer. And so in general, if we have higher density, that's going to be good for us in terms of F layer propagation. So it just says that, yeah, UV photons can generate free electrons in the F layer. And then the recombination times are also another very important parameter. How long do those electrons live before they reconnect with a positive charge and just go away? So then this just shows that what's happening in the F layer right here. So F layer means that the particles, like the nucleuses, are kind of far apart, and the electrons that are become free right here, which are these little tiny dots, are the free electrons right there. So they can live a long time in the F layer. In the E layer, which is much lower to the ground right here, we have a higher density in the atmosphere, and those electrons will not live as long at times. So they're effective. And in the D layer, the lowest layer, let's say an electron might get produced by absorbing a UV photon, but there's such dense close proximity of all the positive charges to each other that they're going to have a very short lifetime in the D layer. Yeah, go ahead.
Besides like the amount of like free electrons in there's one spot, does electronegativity or like other things also affect like how fast they recombine together?
Tell me more about electronegativity.
Oh, that's how much like oxygen is very electronegative, and like so it really wants to become stable compared to like carbon or something.
So it's kind of like you got an electron dancing around and you got a positive charge dancing around, and you're saying that certain molecules, when it gets in close, will
Yeah, because it
match up really quickly.
depends
Other ones that may be a little harder for them to recombine.
depends on like where how the shell's made up, how many layers and the orbitals.
Yeah. Yeah, I think that could affect the lifetime. I don't know much about that, but
I think that affects it quite a bit.
it does, huh? The electronegativity of the positive particle. Yeah.
The density affected.
It's huge.
Well, because I mean, it's really just a factor, or how random it is that an electron can just randomly run into it.
So these plasmas, we have them in the F layer, but we also use them in semiconductor processing, where you put a DC voltage or an AC voltage across a material, and you get a bunch of ionized things, and you then accelerate them in a field, and you kind of, like in this case, you have particles like argon hitting a cathode, and then it knocks off some molecules, and then you deposit it on a wafer or something like that. So these plasmas are very common applications in radio engineering and sputtering systems and things like that. And then there's a bunch of mathematics for plasma. Plasmas look like a really non-dense metal because you got a metal has a lot of free electrons move around, but plasma has electrons, but not at the density you'd have in a solid metal, but it looks like a very non-dense metal. And this is what I was saying before. So if you have a electric field and a charged particle and you have an AC field, it will move, but at higher frequencies, it won't move very much. So I don't know. I think we've gone here for 45 minutes. What kind of attention span do we have here?
Ask the class? Continue, I say continue.
Okay.
No,
I don't think I'll do all these slides because I think
we're halfway done.
yeah, I'm halfway the slides. I think it's too much here. Let's see. So there's these things called the maximum usable frequency, and so for a wave to go through the ionosphere and be re-radiated down, there's a maximum frequency where that is possible to do. And so from the previous slide, all the math was trying to say that there's this thing called the plasma frequency right here. And the plasma frequency is the electron charge over 2 pi over, what is NE right here? Maybe some density.
Number density?
I'm not sure what these are right here. You think there'd be some lifetime in here too. This looks like a dielectric constant. So yeah, E is must be the electron density right here. And so the plasma frequency is 9 times the square root of electron density, probably in electrons per centimeter cubed or something like that. But I'm surprised there's not like a lifetime of the ion here somehow. But there's something called the plasma frequency. It depends on the density of the electrons. And I thought it'd be related to the lifetime too. But a maximum usable frequency is a frequency close to this plasma frequency, which is 9 times the square root of the electron density. And so during day and night, you have different electron densities. So the maximum usable frequency goes up and down for this layer F propagation. And then the lowest usable frequency has to do with the electron lifetime. If the electron lifetime is really long, then the lowest usable frequency goes up, I guess, right? And so below this frequency, if you try to go through the atmosphere, you'll just get mostly absorption. It says if the period of the signal is much longer than the free electron lifetime in the lower D layers, the signal just gets absorbed. So at really low frequencies, you send a radio wave up in the sky, it never makes it to the F layer. So if you try to do something at 20 kilohertz or something like that, it's just not going to make it up to the F layers. You'll never get any sky wave bouncing off the atmosphere, off the ionosphere at low frequencies. There's just lower and higher frequencies, and that's like the golden band for HF. The MUF goes up and down with the electron density. The lowest usable frequency goes up and down with electron lifetime in the D layer. It's kind of like a bandpass filter.
Thank you.
Here it just talks about different plasma frequencies right here. In the F layer, you get a plasma frequency like 15 megahertz during the day, and the lowest usable frequency like 1 megahertz during the day. And I think it must change from night to day too. So frequencies higher than the maximum usable frequency just keep on going. If they're below the maximum usable frequency, they can be refracted back down. A whole bunch of different cases right here. There's one other thing I want to talk before we go, and that is troposphere scatter. Last thing I'm going to talk about. So One thing that somebody mentioned, why can light go above the horizon? I mean, radio waves go beyond the horizon. The first argument was the index refraction is highest at the ground level, index refraction goes up. And so that can tend to want to bend the radio signal beyond the horizon. But the other thing that's really interesting is that if you're in the VHF, UHF band, and the troposphere is like this lower place where you have pretty dense atmosphere. Now, if you have a little cold section of sky, it's going to be a little bit higher index. And if you have a high temperature, it's going to be a little the cold will be higher index, and then the hot will be less index. And so you get index refraction variations, and sometimes it's little pockets. If you're up there high enough, you got a clump of cold air, a clump of hot air, and so there's this effect of scattering. Now, if your clump right here is on the order of the wavelength that you're trying to propagate, then it will effectively scatter. If the lumps are really smaller than your wavelength, they aren't going to scatter too much. But if the lumps are about the size of your wavelength, then you'll get effective scattering. And so at 50, 144 megahertz, almost any time of the day, you can shoot enough power up into the troposphere, and the lumpiness of the index refraction will scatter it, and some energy will come down. It's going to be really weak. And so typically you do this in Morse code, CW, or single sideband, and have really sensitive receivers and like huge powers and really directive antennas. And so probably if you had a kilowatt at your radio station right here, and somebody in San Francisco had a kilowatt, you pointed the same spot in the sky, and there'd be a lot of times during the day that lumpiness of the atmosphere would allow you to talk between here and San Francisco just on troposcatter. And so that is a very important mechanism for long distance radio communication at the VHF, UHF. But they're very weak signals. I guess there's a group of people that meet every week at 144 megahertz. There's a person, M2 Antennas in Fresno. There's a guy that owns that antenna shop, and he has a big ranch up in the hills out there. I think he runs this net, and he'll point his antenna to Southern California, make a bunch of contacts to Southern California, then mid California, then he points to Northern California. And even though this is VHF, they're definitely not line of sight. He has this net every Tuesday that just goes and talks to all the people who love VHF, UHF propagation in troposcatter for the mode. And so I found that very fascinating. This is when I go on these contests for VHF, UHF. The troposcatter is a really big deal for getting long distance radio communications around California. So it's kind of neat. I think with that, I probably held you up enough. So it's really interesting. I hardly covered much of it, and I don't claim to be an expert at all myself, but it's been really interesting just witnessing physics firsthand. I've always been more of a electrical engineering who always enjoyed my physics in high school and everything, and so ham radio is kind of like living physics live. And the fact that you're sending up signals to different areas and bouncing it down, and that's me causing those electrons to go up and down. I think that's just so interesting. Yeah, so that's it for my presentation today.
Didn't you cover this or told this, but like, do you say anything about the angle of attack and what would be best?
Yeah, I didn't talk about that at all, but yeah, there's like at 3.5 megahertz in the middle of the day, it will propagate straight up and down at any angle. So it'll go any angle at all. But it doesn't get up to the F layer. So during the day at 3.5 megahertz, you can make a few 100-mile contacts, but you're not going to get thousands of miles contacts. And I don't think you're using the F layer. Maybe you are, I'm not sure. But yeah, definitely the shallower the angle, the better. In general, I think for long distance communications. Certainly the if you're too steep, sometimes at different frequencies, it's not going to be
Yeah.
bent. It's be bent down, but depending on your angle of radiation, you'll have it come down in different distances. So generally, for long distance communications, we want to have a low angle to have the longest skip distance right here. So vertical antennas are great for low radiation angles. Yeah, go ahead.
I suppose this is in a similar vein. Can you talk about NVIS?
Say again.
NVIS, your vertical instant skywave?
Oh, you tell me about it.
Well, I don't know enough about it. I presume it's something along the lines of you point your antenna directly up and it comes down pretty close by.
Yeah.
So you can, I guess, avoid or be able to get closer radiation with HF rather than going further with more skip.
Yeah, I know it during the day, you can just have a dipole. A dipole at 3.5 megahertz is not very high above the ground typically in terms of wavelength. And so it's going to have lots of energy going straight up. And you can make really strong contacts with people at 30, 40 miles away because the at 3.5 megahertz, it's bouncing almost directly down, straight up, straight down. And almost so yeah, that's an example of that near vertical instance communication. Go ahead.
Did you talk about like meteor scattering?
I didn't. That is really exotic. Yeah. So you have a meteor come in, it leaves an ionization trail, and so you can. There are certain times of year where you have meteors are more common, and then I think that they have. You typically have to do really quick pingy kind of things because they only last a second or two, and so you may send up a little data packet and you might make it there, but then like 2 seconds later, it's gone. And so that was kind of a very exotic communication. There's one time that the military was thinking, okay, that's a totally secure environment, and you have a sensitive on-off receiver, there's probably enough meteor is happening that you might be able to send some data back and forth with being totally secure. But I think right now it's just an interesting phenomenon. Yeah.
Why are the maximums like tapering off?
Why are the what?
Like the maximums like tapering.
Oh, these are the sunspot cycles right here.
Yes. So why is the sun not going as much?
I don't know why is the answer, why do we have sometimes with lots of sunspots and sometimes with very few sunspots?
I think what he means is why is the peak on each cycle is dropping.
Because that's fair.
Well, that's just completely random. And it's like the peaks align with the peak solar activity, but the maroon line is actually just the number of sunspots. And so like during high solar activity, there's a higher chance of sunspots occurring on the surface of the sun. It doesn't mean that it's
Okay, there's just a tiny sample.
right.
Okay.
I mean, it's like yeah, like you will get a peak. It's just you don't.
I
know
just didn't realize
how
you could go from like basically 8 megahertz to like 16. Like that's a big jump.
yeah.
Yeah. Okay, I'm gonna get some more pizza then. Very good.
Thank you.
Yeah, sir.